Hello, and welcome to the lecture on Chapter 4 from the Cosmic Perspective, ninth edition. In this fourth chapter of this astronomy textbook, we're going to do a breakdown of physics. In fact, this is one of two chapters where we have a crash course in physics. In this one, we're going to talk about motion, energy, and gravity. Why? Because these are such important concepts in astronomy. We need to understand the motions of planets, comets, galaxies, and so on, like these two galaxies that are crashing into each other and merging. What are the forces that drive this merger? How can we track energy and its conservation? How can we track momentum? How can we understand this merger through gravity? These are all questions that scientists can answer because of the building blocks that were started 500 years ago that we will discuss in this lecture. So, in section 1 of chapter 4, so 4.1, we're going to talk about describing motion, examples from everyday life. Okay, so how do we describe motion? And, good start, what's the difference between mass and weight? Well, there are some particular terms that we have to get out of the way for describing motion. One of those is speed. Speed is distance over time, and it's measured in the metric system, which scientists use, as meters per second. Okay, as opposed to miles per hour, which you're probably more used to. Okay, so here we have 30 kilometers per hour and then speeding up to 60 kilometers per hour. I know those aren't meters per second, but they're in the same base units because a kilometer per hour is just 1,000 meters per 60 seconds. So the conversion's easy, and we don't have to know how to convert from, say, feet or miles over to the metric system. We're still in it. But that process of the car speeding up from 30 kilometers an hour to 60 kilometers per hour, that's what's known as an acceleration, okay? At least one form of it. You can also slow down. That would be another form of acceleration. For example, going from 60 to 0 kilometers per hour. Now, you know that as deceleration, but we call it negative acceleration, all right? Because it's the exact same physical process. Because an acceleration, by definition, is any rate of change in velocity, which I'm about to define. And since it's a velocity that is changing over time, it is a meter per second, which is equal to a meter per second squared. So those are the units you will always see for acceleration. Now, there's an interesting thing about both acceleration and this term velocity, because it turns out that speed is just a number, but velocity is what's known as a vector. It has both value and direction, and that's really important because we need to know where things are heading, not just how fast they're going. And furthermore, if an object changes its heading, so instead of going, say, due north, it turns and starts going a little bit west of north or east of north, well, in that case, that actually is a form of acceleration. In other words, turning, even if you keep your speed constant, is still acceleration because you've changed your heading, therefore you've changed your velocity, and by definition, acceleration is a change in velocity. And this actually makes sense. This isn't an arbitrary choice because it turns out that the concepts of force, the concepts of that it takes energy and force to turn, you can't do it for free, means that it's really not that dissimilar from speeding up and slowing down. Okay? So, in other words, turning like this is a form of acceleration because your velocity changed. And an example of velocity would be 10 meters per second due east because you know both the speed and the direction. Okay, so with the definitions of velocity and acceleration out of the way, let's give some examples of an acceleration that we're very familiar with which is the acceleration of gravity. Now, to be clear, we are talking about gravity here on the surface of Earth. Gravity differs wherever you are. If you move away from the surface of Earth, the gravitational pull of Earth gradually decreases. We'll talk about that. You have to move pretty far away for the gravitational pull and the force of gravity to decrease substantially. For example, even satellites are well within the gravitational pull of Earth, where the number is not that different from the number that you'll see in these slides. In other words, it's close to 9.8 meters per second squared, maybe 8 or 7. Now, if you move further enough away, then that number will eventually fall off to some tiny fraction, some tiny number. But on other worlds, you would have different gravitational accelerations. But let's get back to Earth. All falling objects accelerate at the same rate. okay? Now that's true of any planet. As long as you're on that planet, everything falls at the same rate, okay? Now, this does ignore any air resistance that changes based on shape and also surface features and so on, okay? But certainly in a vacuum, you can see this behavior very dramatically. And what's cool is you can do that on Earth. You could create a big vacuum, and people have, and drop things like a feather and a bowling ball and notice that they actually fall at the same rate. Because without air resistance, they will. And like the idea is that the rate at which they fall is importantly completely independent of their mass. Okay, so really what would slow a feather down is entirely its air resistance. It doesn't matter that it's light. Everything falls at the same rate. Now you can go to a world like the moon where there really isn't air resistance because there's no atmosphere, and also see it there, because that's exactly what will happen without air resistance, without an atmosphere. Any object will fall at the same rate. Now, the rate of falling on the moon is 1/6 what it is on Earth. So I keep hinting at it. What's the number here on Earth? Well, it rounds to 10 meters per second squared. So what that means is that objects speed up at a rate of 10 meters per second every second. So if an object starts at time zero at a velocity of zero, after 1 second of falling, they're moving at about 10 meters per second. After 2 seconds of falling, they're moving at about 20 meters per second. And I bet you can guess that after 3 seconds, the velocity of the falling object has now sped up to about 30 meters per second. See, it's an additional 10 meters per second every second. That's due to gravitational acceleration on the surface of Earth. Now, we say it's about, and we have all these symbols where it's approximately equal, because the number is more accurately 9.80. Okay? So that's the official number for gravitational acceleration on the surface of Earth. Now, Galileo showed way back in the 1500s that g is the same for all falling objects regardless of their mass. That's just what I was talking about. And there's some good reasons for that. And the reason ended up being proven by Newton, and it falls under the law of universal gravitation. That's the explanation. But Galileo observed it, which is a great start. Okay, couple more important physical quantities: momentum and force. Okay, momentum is a quantity that is conserved, and that's why we care about it. Force is what creates accelerations that can change velocity. Remember, that was speeding up, slowing down, and turning. Okay, even turning at constant speed. So force is very important for creating accelerations. It might be less obvious why we would care about momentum, especially because momentum is a odd equation. It is mass times velocity. Okay, so mass we haven't talked about, but mass is measured in kilograms. Everything has mass except for light, but that's a story for another lecture and another chapter. But everything except light has units of kilograms. It's also something known as inertia. We already talked about velocity, meters per second. That means that momentum is kilogram mass meters per second. Now, if you haven't heard a lot about kilograms, you've probably heard of pounds. Pounds technically aren't a mass, they're a force, but there is a conversion, at least on Earth, directly between kilograms and pounds. A kilogram is more than a pound, but it's also, in the metric system, importantly, 1,000 grams. So that's momentum, mass times velocity, okay? Maybe you've heard of momentum. Bigger objects have more momentum because that makes their mass bigger. Faster objects also have more momentum. But on its own, it's kind of uninteresting. Like I said, why would we care about it? The reason is it's conserved, okay? Which you'll see a bit of. In astronomy, it turns out we talk more about angular momentum being conserved, but that's not a big step for momentum. It's just momentum and rotation. Same idea, right? Same idea of mass and speed, coming together, and that it's the product of the two, right? It's the multiplication, and that quantity is conserved, okay? But more on that later. What about net force, right? What does the net mean here? Well, the net means total. This would be the sum of individual forces. So if you have the force of gravity and the force of friction acting on you and some other force, well, then you have to sum up all those forces to find your net force. And the net force has an interesting relationship to momentum. It changes it. So if your net force isn't zero, your momentum must be changing, okay? And if your momentum is changing, then you are accelerating. All right, so there's a relationship between acceleration, momentum, and so on. Now, rotational momentum, as I mentioned, which is more relevant to astronomy because things don't really move in straight paths in astronomy. Everything's rotating in elliptical orbits or circular orbits or parabolic paths or hyperbolic paths. Everything's moving at angles. And so all that rotational motion, even spinning around its own axis like worlds do, Well, that's angular momentum, okay? And it's the same idea, mass times velocity, but the units are a little bit different. Now, a little bit more about angular momentum. Well, angular momentum describes objects that are spinning or moving in circles. So you have orbital angular momentum, for example, because that's a circle, right? It's a circular orbit. Even if it's elliptical, it doesn't matter. It's still angular momentum. It doesn't have to be a perfect circle. And then you also have rotational angular momentum. So really those, whenever we talk about something, whether it's a moon or a planet or a star, they always have both. Okay, there's always going to be rotational angular momentum around their own center of mass, and then orbital angular momentum around something that they are orbiting, and what they're orbiting is the shared center of mass between them and some larger mass. Okay, and it's just that just scales up throughout the universe. Now, angular momentum is created by a special kind of force, a rotational force, if you will, which is called torque. Okay, so just like force creates acceleration, torque changes angular momentum. Or to make it more directly comparable, just like force changes momentum, torque changes angular momentum. You got that? Force changes momentum, torque changes angular momentum. And if you heard the word torque, think like a wrench, right? Torque is a twisting force. Okay? All right, thought question. First one in the lecture. For each of the following, is there a net force on the object described? Remember that net forces change momentum, which is to say they create accelerations. Okay? So, a car coming to a stop, yes or no? A bus speeding up, yes or no? An elevator moving up at constant speed, a bicycle going around a curve, a moon orbiting Jupiter. All right, so have a yes or no for every one of these five. Pause the video if you need to. Let's see the answers. All right, so it was definitely yes for the slowing down, negative acceleration, positive acceleration for the bus speeding up, but the elevator moving at constant speed, even though it's going up, the fact that its speed is constant and it's not turning, yep, well, that is not a net force, okay? Now, a bicycle going around a curve, even if it's going at constant speed, which was not specified, would still be a force because it's turning. And interestingly, a moon orbiting Jupiter, well, moons are known for maintaining constant speed. They're not erratically slowing down and speeding up, are they? Right? They're definitely not. But they are still turning. So every orbit, from a man-made communication satellite to our own moon or to a moon of Jupiter, is all there. Every one of them is experiencing a net force. So it'd be yes. Now, the elevator, by the way, which is moving up, the reason it doesn't have a net force is because it's a great example of two forces that sum to zero. Because remember, net means total, which is another way to say sum. So in the case of the elevator, there'd be some tension force that's pulling the elevator up, and that tension force is pulling it with an exact same value as its own force of gravity, which is known as its weight. Because the force of gravity is quite literally a synonym of weight. So those two forces together sum to be the net force on the elevator, and they sum to zero because the forces, just like velocity, have direction that matters. So we would say Ft minus Fg. So force of tension, that's the T, then force of gravity, that's the G. They sum to zero, which is to say the net force is zero. So if it helps to see the equations like that, that's exactly what we're talking about. So, okay, we've got some basic terms out of the way. We have defined velocity, acceleration, momentum, force, angular momentum, and torque, okay? And we've made it clear that there's a relationship between net force and, well, honestly, net torque, but I think just to call it torque is fine, and changes of momentum, whether there are just plain old momentum or angular. Okay, so we've seen a lot, that I acknowledge that, but that's what we've seen so far. Now we have a couple of very particular terms we want to know the difference about. And it's kind of interesting because we introduced mass because it was part of momentum, but we haven't focused on mass much, and I think it deserves some focus. So the question here is, how is mass different from weight? Well, let's take a look. Now, mass and weight, they're used interchangeably in everyday language, for sure. I mean, just the fact we can convert from kilograms to pounds, but like I said, one is actually officially a unit of mass, and the other, pounds, are a unit of weight. That's weird, right? Okay, so let's clear it up. What is the difference? Mass. Mass is a measure of the amount of matter in an object. I often think of it as the sum of all the atoms, right? So you know when atoms have a certain fundamental mass, and if you count all the atoms in an object, right, a huge feat for any macroscopic object, well, you know, then it's going to be trillions upon trillions of atoms, but that's the idea, right? That's the actual mass. And importantly, mass never changes because it's what you're made out of. And you're going to be made out of the same thing no matter where you go, even if you go to a different planet. But weight is the force that a scale exerts upon an object, okay? That's how it's measured, all right? Now, that means that it's a pushback force. You stand on the scale pushes back, and it measures how much it has to push back because it's got some sort of calibrated spring or digital sensor inside of it. Well, that's the idea, is you're pushing on it with your gravitational force, and it's measuring that. But it wouldn't measure the same thing when you took it to another planet. You got it? All right? Now, by the way, you are weightless in free fall because if you took a scale with you and jumped out of an airplane, right? Like especially if you ignore air resistance, then you and the scale are just going to go together. If you tried to stand on it, well, you wouldn't push on it, right? Because you're both falling together. So there's no way to push on it. It needs to be on the ground because essentially, in the case of you standing on a bathroom scale, you push on the scale, it pushes back on you. Meanwhile, it's pushing on the ground and the ground's pushing back on it. So you have these force pairs between you and the scale and the ground, allowing you to actually measure your gravitational force. Can't measure it in free fall, all right? Now, that's also why astronauts are weightless, because they're in free fall. More on that later. Okay, so thought question 2. The gravitational force on the moon is weaker than on Earth. This means that on the moon, here are your options. My weight is the same, but my mass is less. My weight is less, but my mass is the same. My weight is more, but my mass is the same. Or my weight is more and my mass is less. Okay, so which is the correct answer? Take a second, pause the video if you need to. Let's see the answer. It's this one. Your weight is less because the gravitational tug on the moon is less, therefore you weigh less. Less gravity, less weight, all right? But you know what doesn't change? You know what never changes? Is your mass. Your mass is the same, all right, on the moon as it was on Earth. And I didn't say it, I meant to, but your mass is the same when you're falling too, right? Free fall, you still have mass, you're just weightless. You're never massless unless you were obliterated, and you wouldn't be you, right? Mass is always conserved. I mean, I guess it can be changed to pure energy. We'll talk about that when we talk about nuclear processes, right? You can also turn mass into pure energy between interactions between matter and antimatter. That's another thing. But regardless, it's still there, right? And even if it changes into pure energy, it's fundamental to the universe. Weight is just relative. It's just how much you're getting tugged on by whatever gravity you happen to be near. Interesting idea, isn't it? Okay, so why are astronauts weightless in space? All right, so I told you why. I said it's why they're falling, but let's explain it, right? Because a lot of people don't know this. All right, so first of all, there is definitely gravity in space. So take the International Space Station. It's about 300 kilometers up above the surface of Earth. Gravitational acceleration there, which I said a few minutes ago, isn't that much less than at the surface. The surface, we got 9.8 meters per second squared. Up at 300 kilometers, it's only going to be about 8.9 meters per second squared. Not a big difference. Now, most satellites, by the way, are not at all to scale to this, like in this picture, right? So there are satellites that are up as high as this silly looking person strapped to a rocket, right? And there certainly are no towers that are this tall. I bring that up because I mentioned the 300 kilometers, a particular altitude for a lot of satellites. It's low Earth orbit. It's about as low as you can put a satellite and not have to worry about any atmosphere. But again, the scale, if that's 300 kilometers, isn't accurate because the Earth, good number to remember, is about 6,300 kilometers in radius, so about 12,000 kilometers across. So you clearly, right, if I was to draw 300 kilometers, it'd be quite small, because it'd have to be, some 30th as big, it's, as the value here, right, or some 20th as big as the value here, the radius. Okay, so you get the point. Anyway, not to scale. All right, but there's definitely gravity in space at 300 kilometers, and there'd even be some at this much higher distance, right? If this is maybe, half an Earth radius, if it was to scale. Okay, well, weightlessness then, because it's not due to less gravitational pull, is just due to the continual free fall. All right, that's great, because we understand free fall. You jump out of a plane, you're in free fall, okay? That you're just falling down, you don't have any weight, okay? Air resistance you still have, whatever, but no weight. But if you fall, you eventually hit the ground, right? Every skydiver has to open their parachute eventually. Every elevator that has a cable brake will eventually hit the ground. Hopefully no one's in it. So things have to hit the ground eventually, don't they? Not so, because if you jump and you go to the side, then you're going to take a big arced path, right? Well, what if you jump off something, jump off a ledge, like, but you go so fast that the arced path that you take matches the curvature of the earth underneath you and you never hit the ground. That's all a satellite is. And that's shown here, right? So we have some giant imaginary tower. People are climbing up to the top, right? You have a couple people who run really fast and jump off the top of the tower. And since the tower is so tall, they might travel a huge distance, but they'll just take an arced path. They run and jump off faster, they'll still take an arced path. But if they strap a big rocket to their back, so they go really fast, right? Not infinitely fast, just fast enough, then they'll still take an arced path. But it turns out that that arced path, like I said, will match the curvature of the earth underneath. They'll never hit the ground. So satellites are just falling objects that are moving really fast to the side. How fast? Well, about 7,000 meters per second. All right, that's the necessary velocity. It depends on how high up the satellite is, but we can take that as a gross average. All right, so what have we learned here? Well, we've learned how to describe motion with speed, which equals distance per time. We've learned that velocity is speed that includes a defined direction. We've learned that any change in velocity, including turning at constant speed, is acceleration. We've learned that momentum is a quantity defined as the product of mass and velocity. We've learned that force causes changes in momentum, which produce acceleration. We've also learned the difference between mass and weight. Mass is fundamental and unchanging. It's a quantity of matter. And weight is just relative to where you are because it's a force acting on you, a gravitational tug. And we also learned that objects are weightless when in free fall, and that means that any satellite, anything that's orbit, is just in free fall, which is why it is weightless, or why we observe weightlessness inside. Okay? And don't forget, we also define angular momentum and torque. Okay, so this is going to be the next section here. I'm going to save this for another video, so you can pick up and learn about Newton's laws of motion in the next video for chapter 4. Thank you so much for watching this first video. Bye for now.